As long as you guys are able to see that. Otherwise, if you guys don't like it, I will just switch to chalk and blackboard, and yeah, you guys can record at your own discretion. I don't mind. ENS 295. That's what everyone's here for, right? Nobody's here for any other course or anything like that. Good. Yeah. This is the first time we're actually running the course, so I'm actually really excited too. I'll give a little bit about myself. My name is Miles. I'm actually an alumni from here. I graduated here in, I want to say 2021. So I did Zoom University basically because of COVID. I had Professor Francelon for dynamics, Professor Dawson for statics. From there, I transferred to Stony Brook University. I got my bachelor's and master's degrees in civil structural engineering. And this was one of my favorite courses while at Stony Brook University. It's a very good course. Hopefully some of you like statics. It's a continuation of statics. Who here doesn't know what the course is about, first of all? Let me ask that. Does everyone have some kind of concept on what it's about, designing of components? It's a fun course, teaches you the basics of certain design components, which are an elementary foundation into more advanced courses. I'm gonna ask you guys a little bit about yourselves as well, just because I wanna gauge what type of engineering y'all are interested in and just see where everyone's potentially planning on going. But anyways, got my bachelor's degrees from Stony Brook University and my master's degree from there. And now I work full-time as a tunnel engineer for an engineering firm called Mott MacDonald in New York City. I work on a wide variety of tunnel projects throughout the US and Canada. One of the biggest projects I'm working on is the Hampton Roads Bridge Tunnel Project. That's a $4 billion dual TBM expansion project down in Norfolk, Virginia. They actually just broke through with the tunneling operations just recently, so I'm very excited about that. But yeah, I guess just that's a little bit about myself. I'd like to learn more about you guys, your interests in engineering, what your plans are for transferring, what majors, and so on. So let's start with you and go around the room.
My name's Liam. I'm considering either structural or mechanical engineering, and any other things.
Nice.
I should throw in there.
What universities do you plan on transferring to?
I'm in the joint admissions program with Stony Brook. Is
nice.
that what you do as well?
Yeah, through civil engineering?
No, not for civil engineering. It's just through the engineering science program.
I'm trying to get I reached out last semester to the chair of the department, so I'm trying to get civil engineering as part of the joint admissions because I know they're a little bit of a pain in the butt for it. But so what did you go through? Engineering science, mechanical?
Yeah, just engineering science.
Okay. All right, that's cool. How about you?
My name's Antonio.
Antonio.
I'm thinking about computer engineering.
Computer engineer.
And I was thinking about either Stony Brook or Binghamton. I haven't decided yet though.
All right.
I'm Hunter Hernandez. Looking for mechanical engineering, and I'm planning on transferring to City College or Tom College of Engineering.
All right, City College is good. They have a very massive engineering program, very old too.
I'm Travis. I'm trying to go for mechanical or aerospace because they're kind of similar in some places. Looking at Buffalo or RTT.
All right, nice.
My name's Kevin. I'm also doing mechanical, and I'm probably going to go to Stony Brook.
Stony Brook?
Yeah.
Nice. Stony Brook's very convenient. I'm always going to be biased towards Stony Brook because I went there. How about you?
My name is Trevor, electrical engineering, and I'm going to Stony Brook.
Stony Brook. For electrical engineering, sure, right? Yeah.
My name is Josh, and I'm thinking of going for mechanical engineering.
Where about?
I don't know yet.
Don't know yet? You got time still, don't worry. How about you?
My name is Andreas, and I'm planning on doing mechanical and civil at Stony Brook.
All right. Anyone in the class? What are you guys asking for? All right. Hi. Those are my students from last semester. I taught strengths and materials in the construction tech program also. Repeat what you said, I'm sorry.
My name is Andreas, and I'm planning on doing civil and mechanical slowly. Stony Brook Farm. Yeah.
Stony Brook? Nice.
Stony Brook Indeed.
All right.
I'm Ryan. I'm gonna probably do mechanical and I plan on going to either Buffalo or Binghamton.
Okay. How about you?
My name is Brianna. My interest is civil structural engineering, and I'm thinking Manhattan College, which is not Manhattan University, I think, in the city.
That I don't know. I know when I applied there, it was Manhattan College.
They changed it, I think, this year.
Oh, they got upgraded.
Yeah, so Manhattan College or Buffalo.
Nice. And then last but not least.
I'm William, mechanical engineer or electrical, not sure yet. Probably going to Buffalo.
Nice. Now, hopefully everyone wants to get professional licensure in their fields of engineering. I'm proud to say that as of this winter, I have passed my professional engineering exam. So because of that, I just now need to satisfy the work experience requirements. I basically went through New Jersey for the licensing because New York, you have to submit your work experience, which I don't satisfy yet. I have I want to say another few more months before I technically meet it, but New Jersey lets you take the exam basically near immediately after finding out your FE exam results. So that's a good tip to know is if you want to try and get the PE exams out of the way early, go through New Jersey or another state. The exams are entirely online now, so it's you can take it anywhere. All right. Again, you just walked in, so how about you give us a little introduction about yourself, what you're interested in terms of engineering, what school you plan on transferring over to.
So my name is Matt McCarthy. I'm actually a third-year student. This is my first year as an engineering student. So I was previously in physical education and kinesiology. I wasn't loving it. Took my first physics class and kind of just switched over immediately. Changed my major and everything. So I'm looking into mechanical engineering. I previously went to SUNY Cortland, so I'm looking to go back there with a new major next year probably, but yeah, that's about it.
Nice. All right. Now, did you, any particular reason why you switched to engineering?
So in kinesiology, you have to take physics 1 and 2, and I took physics 1, and that's the best I had 4.0 in that, and as soon as I saw that grade, I was like, you know what, maybe I just had been in the wrong major.
Nice.
So that was that.
Cool. And did you say what type of engineering you wanted to go into?
Mechanical.
Mechanical. All right. I'd assume the majority of students here are mechanical or civil. This is a good course to be taking. It should meet course equivalency once you're transferring. I know right now it's kind of hey, how's it going? Right now I know it's sort of like one of those special topics courses, but we're anticipating it'll transfer. I stole half the material from Stony Brook anyways. So, I literally have all my notes from when I was at Stony Brook. It's just going to be a copy-paste, basically. I'll probably just... Only thing that'll be different is, exams and maybe some of the examples that I do here. And since you just walked in, how about a little bit about yourself? I know you're an engineering science major. What type of engineering you're interested in?
I'm interested on structural engineering.
Structural. Nice.
Yeah. And I'm only coming to Suffolk for this one class because I already graduated.
Mm-hmm.
But I saw the class, so I wanted to take it.
Yeah. And you plan on transferring somewhere?
Yeah, Buffalo University.
Nice. Yeah, that's one of the nice things now, I guess, about this course being offered here is because I know when I transferred in the fall semester. So because of that, I was able to take strengths and materials at Stony Brook, which is only offered in the spring. So because of that, at least when you guys graduate, you could just enter junior year without any issues at your other universities. Whereas I know I had some students who, not students, but friends who transferred from here who had to take it during the summer, and this is not the course to be taking over the summer. No worries. All right. I think that's everyone, hopefully. How about name, major, where you plan on transferring?
Christian Unroth. I plan on going to Binghamton for mechanical engineering. Sorry.
No worries. We haven't even started yet. It's first day, traffic and snow. It's 5 o'clock. I got here at 2 o'clock because I don't want to sit in rush hour. All right, so let's get into it. So this first course is Strengths and Materials, first time that we're offering it. Today, I'm just going to be going into the introductory topic, which is going to be the concept of stress. Now, you guys remember from statics, what were the equations that you guys remember from statics? It's just equilibrium, right? Sum of the forces in X, Y, and Z equals 0. Sum of the moments equals 0. The math might be a little bit convoluted at times, but all the concepts are the same. Now, that course taught you equilibrium, but it didn't necessarily teach you how to design stuff. It didn't teach you how forces transfer, dependent on stiffness of materials. It didn't teach you how to design for said materials or said beams, columns, or whatever. Now, the way that we do this is, what we need to do is we need to calculate what we call a normalized stress or a normalized value of force. Everyone can see my handwriting okay, right? It's all good? All right. I just want to make sure not that it's too sloppy or whatever, because I could probably, for the next class, find some of the old PowerPoints from Stony Brook and just present those. But I know I like to do this just by hand, just because then I'm not you guys don't feel rushed to write everything down. All right. Now, what is the point of this normalized value of force? It's to evaluate the carrying capacity of members of different sizes. All right. And one of the key equations that we use to do this, the way that we use to normalize stress, is by using the geometric properties of said given beam or column. So, in summary, stress is just going to equal a force divided by some area. And that's basically just the definition of normal axial stress. From statics, what you might have seen is a problem where you have a beam, which is subjected to some force here. We could call it P. And it's loaded at some angle alpha, right? So the way that you would solve for it is you would draw out your reactions. You would have your moment reaction. You would have AY, AX. You would break up this force into its components. Right? So we would have PX and PY. And then once you write your equilibrium equations, you would have forces in X equals 0, forces in Y equals 0, and forces in Z equals 0. And from this, we would get AX is equal to P cosine of alpha, AY is equal to P sine of alpha, and then the moment about A is just equal to P sine alpha times its perpendicular distance, L, because it's the length L of the beam. Now, when it comes to strengths, the way that we analyze basically every single member is we need to analyze internal forces. Did you guys cover trusses last semester? Yeah. You guys remember how you would need to cut sections through like each and every single element, and then you can analyze the force that's carried by each member? Those are internal forces. That's a very early introduction to analysis of internal forces. Right? So for trusses, you had like the axial loads, but for like a bar like this, where you have your force, P, and the angle alpha, you would also you would be wondering, like, what is the internal force here? Well, you could cut a section here. And this section can be located at distance x. And then from there, you can analyze the internal forces. You would have shear force, which we'll get into later on in the semester, an internal moment, and then potential internal axial forces. And that's just by cutting a section. So all of this would basically just, again, get cut. And then from there, you can analyze all of the internal forces accordingly, with your reactions being on the left-hand side. MA, AX, or AY, and then AX. All right. And then obviously you would use statics to analyze this and determine equilibrium equations for the internal forces, which then allow you to determine the maximum forces felt by members. Now, this is a little bit more advanced right now. We'll get into it later on in the semester and how to draw what we call internal force diagrams, which basically allow you to see the force at a particular location in a beam or in a column. But right now, we're just going to explicitly deal with axial loading. And for axial loading, we calculate what's called the normal stress, which we call sigma. It's the Greek letter. Now, this Greek letter sigma is the term for stress, which we know stress is equal to force divided by area. So by deduction, you can say that the stress is equal to N divided by A, where A is the cross-section of the member, N is your internal axial force, where N is always perpendicular to your cross-sectional area. Now, it's not always as simple as this. Stress can be dependent on position. We don't generally go too much into this per se until later on in the semester, but without a computer to analyze how the stresses look exactly, because depending on the loading conditions, your stresses can be uniform, non-uniform. We generally just assume uniform stress. And all this means is if we have like a cross-section like, I don't like that, but we could just have a cross-section, looks just like that, and there might be some force applied that's causing tension or compression. Then the internal force that's carried is just going to be uniform throughout. Simple as that. Now, this ultimately makes an assumption that the load is centered on the cross section. But later on in the semester, what I was saying about more complicated loading situations, we can have something called eccentric loading, which just basically accounts for some type of moment arm, which in turn results in a change in how the stress distribution looks in the cross section. So a good example of this might be if you have a long rod just like this, and then instead of your force P being located here, it's like located right here, which then you would imagine the stress being larger on the bottom of the member versus being uniform. So your stresses might look somewhat like this. It could be 0 at the top, it could even be in tension at the top. It all just really varies on the magnitude of the load and the geometry of the cross-section. So ultimately, there's a lot of consideration that goes into the analysis of stresses. Now, let's talk about the concept of stress at a point, which is ultimately the math that we're going to be using for calculating stresses. So let's consider just a circular rod as such. I also just take a time to try and really draw a neat diagram, so please excuse me if I am very slow at that. You might not be able to see that. Yeah. Yeah. All right. So if we look at a load, whoops, and let's say this load is applied directly, we'll call it delta P, so it's some infinitesimal force in a particular area. The total cross-sectional area of the rod might be like this little area here, delta A. And then as you add more and more of those areas, like you could add little rectangles, more and more of them, as you sum all of those areas together, you get the total cross-sectional area. So the sum of all the areas is just, of all those little areas, is just one big area, right? For the total force in the cross-section, P is just going to be some area. It's just going to be the same thing. Each area, each small area is going to have its own independent little force, which then we break up into tiny forces, sum them together, you get the total force. Right? Now, as we get smaller and smaller and smaller, we get into a calculus concept of things. So the normal stress at this particular point is just going to be the limit as that area in consideration approaches 0 of that force divided by that area, we say is just equal to the differential of the force over the differential of the area. And then from there, if you want to calculate what the total load is acting on the structure, or the total internal force, you can break this up and write it out as such. Whoops, I am skipping a whole bunch of steps. right? You guys would agree with me? You can take that stress by rewriting the equation. So you have your force term is equal to stress times the area. That's basically what this is, right? Just written in more of a calculus term for small areas. And then from there, we can just set this equal to the integral of the area times the differential of the force over the differential of the area times the differential of the area. But we know that the stress is equal to the differential of the force over the differential of the area. So you can just simply write sigma times dA. It's whatever the stress is multiplied by the small area, whatever the stress is at that particular point. And obviously you get more and more accurate answers as you go smaller into this. And yeah. And that's basically just the concept of normal stress at a particular point. Are there any questions about this so far that anybody has? I don't know if I'm going too fast or not fast enough. First time teaching an engineering level course, so. Yes?
Would I be able to pass this class if I never took statics?
I think you can, but you're going to have to work hard at it. The thing with this course is I'm not going to focus so heavily on giving you guys heavy statics problems, because I know like some of those statics problems can take like 10, 15 minutes, 20 minutes to solve, you know, and this class is only an hour and 15 minutes. So like, I mean, like if you didn't take statics, I would say don't worry so much about it. I would say definitely try. You're taking it simultaneously, right? Nope. That's interesting. Fun. I'd say you'll probably struggle a bit, but I don't think it's impossible. I would say just work hard at trying to understand the statics behind certain problems, understand force equilibrium, even if at an elementary level, because I'm not going to be giving you guys too many 3D problems to solve. My goal is not to reteach you guys statics. I'm hoping everyone here has a good grasp of statics coming in from last semester or whenever you took statics, so yeah. All right, so we also have other types of stresses other than normal stresses. Another type of stress that we have are shear stresses. Shear stresses are derived similarly to the normal stresses, so I'm not even going to go into the math of it, but the main thing that I want you guys to understand is that shear stress we define differently as normal stress, where shear stress we use Greek letter tau. The shear stress, we calculate the average shear stress, and we set this equal to the shear force divided by that area. Now that area is basically the same area of the cross section of the material that we were dealing with. So if you guys look up at this beam here, this entire beam may have one entire cross section. That's it. Same thing for both. You don't need to change the cross-sectional area at all for it, except until we start getting into more complicated topics. But right now, don't worry about it. So the shear force divided by the area is what we call the shear stress. And it's often incorrect to necessarily assume that it's uniform. So but we do it anyways. A really good example is if you have like a rectangular beam here and it's subjected to some shear force V in the cross section, then how the stresses will look is actually going to vary quadratically. Which for a rectangular shape is 3/2 tau. You don't need to worry about that really too much right now. And then obviously the shear stresses are 0 here. Whereas the assumption we use right now at the beginning is just an average. Any questions about that? Nope. Awesome. All right. So, with all of this in mind, let's jump straight into an example that I may or may not have stolen from Stony Brook University. All right. And let's say that this example is basically I'm trying to figure out how to draw this like neatly. I guess I'll work on this end. Is it grabbing? No. You have a rectangular cross section here. And with this rectangular cross section, it's going to be connected to another set of 2 plates. I'm going to draw those other 2 plates in a different color just so you can kind of see. And that's an awful color. Do orange. I'll adjust everything eventually. Please excuse my atrocious artistic ability. I never said I was an architect. And then I'm going to move this up. Then I'll just erase this. So here we have some type of overlap L. It's some glued on each end here. Top and bottom. Each plate has a dimension W and a thickness T. This thickness T is 0.25 inches and the width is 2 inches. And it's a typical dimension. All right. Now, if I loaded this point here, I know it's a little hard to see, this point right here, with a 10-pound force, what I'd like to know are 2 things. The stress in each for all, and then the average stress that's present in the glue. All right. We can determine the statics of this, right? Like, what would you say the equilibrium would be? How would you guys figure that out? I'll draw a nice diagram on the side. That'll probably just be a lot cleaner to deal with. Draw out everything as is, with the colors, schemes, and everything too. And then black here. It's about 10 pounds. This dimension here is L. How much force do you guys think is going to be carried by each of those orange blocks? Any takers?
Oh, wait, they're glued, right?
Yeah, but total, how much force has to be carried by that wall to prevent the entire thing from pulling out? 10 pounds, exactly. It's going to be split evenly between each block, right? So 5 pounds piece. Like it's a symmetric shape, so it's pretty easy to kind of deduce it's going to be 5 pounds. If they were different materials, forget about it. That's an entirely separate problem. So you could cut sections through each material. So if you cut a section through there and solve for the internal force, let's call that N1 and N2, you would find that N1 and N2, guess what, are 5 pounds acting in tension. And so the stress in materials 1 and 2 is just going to be what? What's the cross-sectional area of those orange blocks? You can calculate that pretty easily up here. Yeah?
0.5 inches squared.
How do you get that?
I just did 0.25 times 2.
Yeah, exactly. So the area is just going to be the 2 inches times the 1/4 inch, which is just 0.5 inches squared. So 5 divided by 0.5 inches squared gives you a stress of around 10 psi. Everyone sees how I got that, right? Great. Now if we cut a section through B and we analyze the internal forces, we could actually take everything from the left-hand side or the right-hand side of the section, right? You guys hopefully remember from method of sections, you remove everything to the left or to the right of the section. Just saying that and hoping you guys know what I mean. Not that I have to redraw this every single time. We get that the internal force in member 3 has to be 10 pounds in tension. And so sigma 3 is just going to be the 10 pounds divided by 0.5 inches squared, which gives us 20 psi. It's carrying double the load, so it's going to be double the stress. Everyone understand how the normal stresses were calculated? Awesome. What do you guys think about the shear stress in the glue? Let's say this length needs to be like 2 inches. What would the area be then? Is it the same thing? You're shaking your head no. Yeah.
Would it just be 4 inches squared?
How do you get that?
Because you take the width of the 2 inches and the length of the 2 inches, multiply them together, you get 4 inches squared, and that's the area of the shear.
Awesome. Right, so the area for the shear, I'm going to just denote it AV, just a little subscript to indicate it's a different area for this problem. It's just going to be the 2 inches times 2 inches, which is 4 inches squared. All right. And we have glue top and bottom. So then my question now becomes, what's the force we use to determine the shear stress? We know what the area is of one thing of glue.
Would it just be the 10 pounds, but divided between the 2 points of glue?
Exactly. Or you could say that each layer of glue carries 5 pounds. Both of them will mathematically give you the same thing. So in the end, you can say that the shear stress is just equal to 5 pounds divided by 4 inches squared, or the 10 pounds divided by 2 layers of that glue, which will just give you 1.25. Is it 1.25? Yeah, should be 1.25 psi. That's 5/4, right? I'm not like losing my mind. Yeah. And that's shear stress. Let's do another example. Snuck up behind me. I should lock that door. All right. I'm not going to draw the 3D shape. I'm just going to do a 2D shape. Let's say it's very similar configuration to how we had it previously. So I'll draw the orange blocks just as we had previously. And then the black block. But now, let's say instead of it being held by glue, it's held by like a bolt that goes through it. I'm actually going to shade this bold light blue. Everyone can see that, right? Yeah. All right. Most bolts will typically have some type of head and then like a nut system. And this will be a 1/2 inch diameter bolt. Does anything change about the normal stresses within each of the members? Those being 1, 2, and 3. Does anything change about the axial forces in those members? No. What changes though? Only the thing that's connecting them. So how do we determine the stresses now acting on the interface of the connection? Yeah.
Would the cross-sectional area of the bolt rather than the glue be different?
Exactly. You would use the cross-sectional area of the bolts. So, bolt, obviously circular cross-section. Hopefully everyone knows the area of a circle. Pi/4 d squared. So pi/4 times 0.5 inches squared. That gives you, let me double check it. Yeah, about 0.20 inches squared. And then similar to how we had it with the glue, that's obviously an area per plane of shear. We have two planes where shearing is occurring, this plane and that plane. So because of that, you would just write tau is equal to 5 pounds divided by 0.20 inches squared, or 10 pounds divided by 2 planes of shear. And that should give you 25.46 psi. And then obviously with those stresses, you can determine like a type of steel that you need. So most steel grades, like if you went with like a stainless steel bolt, for example, they generally have a strength of like 30,000 psi. So obviously like this is any type of bolt will really do. Any questions about that? Nope. Awesome. We can also have other types of stresses, including bearing stresses. For those of you who like civil engineering, a good example of this would be a foundation footing acting on soil, bearing on soil. But bearing is basically when surfaces touch. And this touching results in a contact pressure. Which induces a stress, which is what we call the bearing stress. Now, this is just another type of axial stress, because if you think about it, one surface touched with another surface is just going to induce some type of normal stress transfer through the transfer of normal forces. So you can think of it as another type of normal stress. All right, I got another example for you guys now. A lot of examples. I'm just throwing everything at you. All right. Let's say you've got like this cantilevered kind of truss system kind of going on. And this here has a diameter of around 20 millimeters. So that's obviously circular in cross-section. And then this is 50 millimeters by 30 millimeters. And it's like rectangular in cross-section. So this would be the 30, that would be the 50. Lastly, we need some dimensional requirements. So this will be about 600 millimeters, and then this will be about 800 millimeters. And then of course you need a load of around 30 kilonewtons. All right. Now, I'm just going to test you guys a little bit. I want to see if you guys can solve for the reaction forces. I'll call these points A, B, and C for consistency. They all behave, A, B, and C, as basically pins. So maybe not the best diagram to show you guys, because you guys are used to seeing the triangles, right, for the pins. It's not grabbing it, darn it. So I'm just gonna just redraw it as such. All right, so take about 5 minutes. I want to see if you guys can just solve for the internal forces of each member. You can work together if you want. And everyone's aware with how long these problems should take on a PE exam, right? 6 minutes on average. And you get 80 of those questions. Some of them more difficult. All right, that's 6 minutes. Everyone should have an answer. All right. So, hopefully you guys saw that it was a 3, 4, 5 triangle. And that would have simplified the process and cut down about 5 minutes of time. If it didn't, no worries. I have all the steps here, but if you saw that it was a 3, 4, 5 triangle, we would have went about our day. So, you could figure out the resultant length of AB, or BC, sorry. So BC is just basically going to be 600 squared plus 800 squared. Take the square root of that. It's equal to 1,000 millimeters. You can use proportioning to figure out your forces. So the force in member BC is going to equal 1,000 millimeters. Set that equal to 30 kilonewtons divided by 600 millimeters. And then you can set this equal to BCX over 800 millimeters. And this all comes from just force equilibrium at joint B. So 30 kilonewtons BCY, BCX, and then AB, yeah. Right. Everybody sees where those proportions come from. If not, no worries. I'll just ask me and I'll go over it after class. But once you solve this, you get that BC is just equal to 50 kilonewtons acting in tension. And then BCX is going to equal 40 kilonewtons, which then when you do forces in the x direction would lead you to find that AB is equal to 40 kilonewtons in compression. Great, that's the statics. Now, let's say we wanted to find the stresses in each of the rods to validate what the if the loads were adequate, all right? Now, let's say that the strength of all the materials, the allowable stress, was 165 megapascals. So that's the maximum stress that all of these materials can handle. All right? Well, we just check the stresses now. So the stress in member AB is just equal to the internal force, which we calculated as 40 kilonewtons, right? And then you divide that by the cross-sectional area, which for AB is going to be 50 millimeters times 30 millimeters. That's this area here. Right. And then just multiply it by 10 to the 3 to convert the kilonewtons to newtons, just because newtons per millimeter squared is the equivalent of megapascals. And this should give you 26.67 megapascals. Is that below 165? Yeah. What does that tell us about our design for that member? It's good. Now let's check member BC. The force was 50 kilonewtons again, multiply it by 1,000 to convert the newtons to kilonewtons. And then use the area of a circle. So pi over 4 times 20 millimeters squared. And this will give us a stress of 159.2 megapascals. Much closer, but is it a safe design? Yeah. A lot of times when you're given an allowable stress, there's usually a factor of safety already associated with it. So the true stress that the material can handle is probably closer to like 300 or 400 megapascals. There's usually large factors of safety, which we'll get into next class on what that even is. Everyone's heard that term though, right? Factors of safety. Professor Dawson's probably brought it up. Nice. All right. Well, that's how you design the members. But now there's just one issue. Is we assume everything is a pin connection, so what do we got to do? We got to design the pins now. So I have some sample details here of what each of the pins look like. So for member C, I drew out that the connection detail looked basically like you had a pin here, and then that was basically the rod, which from a top view, this is from like a side. And then from a top view, it might look something like this. That's the wall. And that's like your pin. Everyone see how that kind of comes into play, right? So let's say that this pin, D, is 25 millimeters in diameter. And we basically just want to determine what type of stresses are first acting on here, and then if the size is adequate. For the pin, what type of stress is acting on it? Or stresses, I should say. Shear stresses within the pin themselves. What else? Yeah. Bearing stresses. Between the members themselves and the pin, there's an interface. To determine the bearing stresses, you would generally need some of the dimensions. So let's say that this is about a ½ inch. No, we got to do something that's like metric. Yeah, let's say that this is about another 20 millimeter plate. And then obviously the diameter here is 20 millimeters. So I just chose that conveniently. All right. So the area subjected to shear, we know that this is 50 kilonewtons in tension. The area subjected to shear is just going to be what? Just the area of the pin, right? So pi over 4 times the 25 millimeters squared. I just realized this is physically impossible. Is it? Wait, yeah. That's interesting. That's a good note. I'll have to email him about it. The pin is actually larger than the bolt. Oh no, never mind. Never mind. There's good details for it. I'll show you guys like some of the PowerPoints after class so you can actually see why it's like that. Yeah. So pi over 4 times 25 millimeters squared gives you 490.87 millimeters squared. And then you can calculate the shear stress in that bolt. 50,000 newtons divided by the 490.87 millimeters squared. That's equal to 101.9 megapascals. Here, let me see if I can't actually pull that up now. And if you guys want, if you guys prefer next class, I'll just keep refining these PowerPoints. If you guys prefer looking at the PowerPoints instead of just the lecture notes, that's if I can connect to the Wi-Fi. Let's see. And SEC Public. Either way, I don't want to waste too much time looking at it. Right. So the reason for that is because a lot of times when you have like circular pins like that, usually it doesn't exactly generally look like this per se, but it might be rather something that's like larger, and then it's just like circled like that. So that's the reason why it's larger. Right. Now let's say it's a similar detail down at the joint A. So for A, I'm going to redraw the detail again. But this time what happens is it kind of like tapers off like this, if it wants to draw. And then this is your 50 by 30. Where that's the 30 millimeter dimension. Again, the axial force was 40 kilonewtons. And then you would have a bolt located here. All right. So, really quickly, what stresses are acting on here again? Shear and bearing, right? If I gave you guys the dimensions of this, you guys could determine the bearing stresses. It would just be whatever the thickness of that plate is multiplied by the diameter of the bolt. And then you also have the shear stresses here. Let me actually draw out the bolt just so you guys can really see, like from a far detail. So here's where the bolt is. That's a plane of shear. Shear. And then obviously the planes at which bearing is occurring would be here. Here. Nope. Wrong way. Here, here, and then here. Everyone sees that, right? That's because the force is acting in compression, so this would press up against here, which in turn would press those against that. All right. We could calculate what the shear stress is. So tau would be 40,000 newtons divided by 2. Let's say that the bolt diameter is, again, 25 millimeters, which would make the area 490.87 millimeters squared, which gives us a shear stress of 40.7 megapascals. Now, one thing I want to note is that there's a big difference between the condition here and the condition that I listed here, where if we redrew that shear distribution here, so let's say that that's the stress, this would be a plane of shear. And then obviously this force is 50 kilonewtons. So then obviously this would be a bearing surface. This would be a bearing surface. And the main difference between this is we generally call this single shear and double shear. So if you work an internship, do calculations, and the engineer asks you, is the connection in single or double shear? That's what he's referring to, is how many shear planes are there. Yeah, I think we'll end it there because there's not too much that I can really talk about in 2 minutes without, I guess, going too heavily into detail. So I guess we'll pick things up next class, and then I'll try and hop into like chapter 2. I'll continue working on the problems, and then maybe next class I'll do it with the PowerPoints, and then just ask you guys which you prefer. If you guys like working with the PowerPoints, or if you guys like working with me doing it by hand. So, yes.
Are you going to post the lectures on Brightspace?
Yes, all lectures will be posted on Brightspace. Yes.
And then can you post the PowerPoints too on Brightspace as well?
I will.
All right, thank you.
The textbook, you want us to get it, should we get the textbook online? Or?